And with that, I'll go ahead and hand it over to David.
Thank you, Aurora, and good morning. So today we're going to follow up our previous webcast which covered an introduction to Redshift. And of course, we need to go a lot deeper to really look under the covers and see how Redshift operates. So with me today is Vidya, who's the Senior Product Development Manager for Redshift. And so we're going to take you through some of the details underneath the hood of best practice for Redshift. Now you will have noticed the difference between the invitation and the slide is the words part one. What we realized in building this content is that, and with the feedback from a lot of our customers through our support channel and so on, is that there is a lot more that people need to understand to get their head around and their arms around Redshift. So we will be doing a part two. It's not a teaser with no ending. There will be another one, as well as others in the series. So let's just talk about the agenda. I'm going to do a very brief introduction, I promise, and hand it over to Vidya, who's going to take you through some of the detailed architecture and best practices of Redshift, and we'll leave plenty of time for Q&A at the end. So please queue up as you have questions, as they pop into your head, go into the Q&A panel and type them in there, and we'll get to them in roughly the order that they come in. So a quick introduction. Database services is part of the core foundation services of AWS. It really comprises the structured, scalable, high-performance storage, really for applications. So besides Redshift, we have DynamoDB, the NoSQL high-performance non-relational database for really extreme scalability. And if you watched Werner this morning, he announced an exciting addition to that, where we are releasing local secondary indexes for DynamoDB. RDS is our relational database service, managed database service, constantly adding features, supporting Oracle, MySQL, and SQL Server today. And of course, Elasticache in-memory caching, really a managed Memcached service. So today we're going to focus on Redshift, and specifically, I want to start with talking about the objectives, the motivations, what was the design principles when we built Redshift. It was really very simple. In a mature market, we had to be faster than a row-based store, which was really a low-cost, high-quality data warehouse entry-level solution for many customers. But it had to be a whole lot cheaper than the existing MPP architectures out there, which are very fast, but they're also quite expensive, and a lot simpler. Simplicity is a key attribute, and we'll go through some of that, and you'll understand, if you haven't already, how Redshift changes the equation. Okay, so an important factor about Redshift is the way that it dramatically focuses on the reduction in I/O, which is the essential element for a data warehouse. So there are a number of attributes here of Redshift that enable this. First, the storage is attached. So Redshift is only dependent on network and power for its operations. The data block sizes are large, which allows us to move data between the storage layer and the instance very quickly in large chunks, which is great for those access patterns, those large queries. Most important is that it's a columnar data store. Now this is a structural organization that allows you to put data adjacent on the disk in columnar order. And really what that does, it means it's optimized for query patterns that are heavy on the scan, which are things like large aggregations, billion row queries, things like that. Data is compressed largely as a result of that columnar storage, highly compressible. And the zone maps is a feature which allows us to do block skipping. Now why I'm introducing these, because they're actually, this sort of information is very important to understanding how best practices are enabled in Redshift for making queries and making data ingestion faster. Zone maps, for instance, comes into that heavily when we talk about the way we sort data. Redshift on top, underneath all that, was built on optimized hardware as well. The hardware was built for Redshift. It's since been made available in EC2, so you can spin up an HS1 8XL instance and enjoy. Redshift is a managed service, uses that instance, but of course adds a lot more to the equation, and we'll go into some of that as well. Data protection being high amongst that, but as well as a lot of performance. Redshift runs in HPC, our fast network for high-performance computing, and has extremely high disk density. So that means you get a lot of bang for the buck when you're using Redshift in terms of data storage quantity. You can scale with the instance classes up to 1.6 petabytes, and you can start as low as a 2 terabyte instance. Now, Redshift really is designed to address the gap between data that is generated in organizations and data that is made available for analysis. This is an ever-widening gap, and largely as a result of the cost to close that gap and the effort. And what we mean by that is it can be expensive to move data from an operational data store into a warehouse, and it can certainly be time-consuming. And that, of course, has an associated cost with that. And so with that is the limitation that many customers are faced with picking and choosing their premium data as that which they will put into the data warehouse. So Redshift aims to change that equation in a number of ways. One is to make it super agile and very fast, easy to spin up a cluster, move data in, resize if you need to, with just a few clicks of the mouse. On the other hand, it's also designed to be priced for analysis of all your data. So really two metrics there, 85 cents an hour for on-demand will get you a 2 terabyte instance, and of course you scale it by each of those instances. So 4XL will be 4 times that number. So that's a low on-demand rate is great for assessing Redshift, for understanding if it fits your needs. For persistent workloads where Redshift is a good fit, and if you decide to put your workload into Redshift permanently, or at least 1 or 3 years at a time, that price comes down dramatically. And what the reserved instance is allows you to buy with a small upfront payment, allow you to buy the rate down so that the net effect is dramatically reduced. So 50 to 70% reduction compared to the on-demand price. So that 3-year reserved instance gets below $1,000 per terabyte per year. So what I'd like to do now is hand it over to Vidya, who's going to take you through some of the more technical details of Redshift and focus on best practice, and we'll come back at the end and do some Q&A. Vidya?
Thank you, David, and welcome to this webinar. So I'm going to take you through some of the high-level architecture of the service, as well as some hints and tips and best practices based on what we have seen as common pitfalls for early beginner users of Redshift. If you've been using this service for a while, you'll probably figured out a lot of this on your own, but this will give you an overview of the key things to keep in mind as you bring your workloads to Redshift. Also, to level set, my slides are not nearly as pretty as David's, so it's going to be very verbose and content heavy, so we'll just get through that. So let me start with the architecture. So what is the Redshift architecture? When you go to provision a cluster, the first thing that you do is specify how many nodes you want to use. So let's just take a step back. So Redshift as a service is composed of a bunch of different clusters. These clusters are nothing but machines that have the capacity to communicate with one another, and it stores your data. If you drill further down, every cluster is composed of all these nodes, and you can think of each node as an entity that has dedicated CPU, dedicated memory, and some disk. In fact, drilling even deeper, every node is further subdivided into a number of slices, and each slice has a dedicated core, memory, and disk. So as a service at a high level, it's a bunch of clusters. Clusters are a set of nodes, and nodes are a set of slices. Furthermore, if you look at the nodes themselves, there are two types of nodes. There is a leader node, and there are a whole bunch of compute nodes. When you create a cluster, you will be asked to specify how many compute nodes you would like to provision, and based on your storage needs and performance needs, you're going to pick a number. So every cluster gets one leader node, and these two types of nodes have very different functions. So let's look at each one at a time. So the function for the leader node really is to be the point of contact for the outside world. So it communicates with all the clients, all the SQL clients. It's the single SQL endpoint for all the clients. And within the cluster, it plays the role of coordinating among all the other compute nodes to get the job done. And there's a specific reason why we've architected it this way. This is primarily for security. We don't want, since the compute nodes have all your data, we don't want anyone from outside AWS to have direct access to the compute nodes. There are some exceptions to this, of course, which I'll go through. So the leader node is SQL endpoint. It is Postgres based, so it should work with clients that are compatible with that. And it also stores all your metadata. So when you go in and define tables and users and all the metadata for your database, the leader node tracks it and stores it. The other major function for the leader node is to get your queries and then compile them and generate the code that is needed to actually execute them. So leader node does this and then ships off all the generated code to the compute nodes for processing. And finally, after the processing is done, the leader node still has to collect all the pieces, do any kind of final aggregations or any other roll-up functions, and then send the results back to the end client. So fairly important set of actions for the leader node there. Now let's come to the compute nodes. So you can think of the compute nodes as the storage layer for our cluster. So it holds all the data. The leader node really does not hold any of the user data that you enter. So the compute nodes hold all your data in columnar format, as David mentioned. As well as one key design point for the compute nodes is we want all the big operations here to happen in parallel, because that's what gives it the scalability. So for the compute nodes, we want the queries to process in parallel. It's architected to do that. We want loads to happen in parallel. We back up all your data regularly. All of that happens in parallel, and so does restore. I haven't mentioned this here, but even resize happens in parallel. So when you resize your cluster, essentially a new cluster is created with the new number of nodes that you want, and the compute nodes of the old and new cluster actually transfer data in parallel to speed up that operation. Additionally, all the data here is you have three. So whenever you load data into Redshift, you get three copies. One is the primary copy that gets onto the compute nodes and to the disks there. Within the cluster itself, we actually store a mirror of the data, a secondary copy of the data. So in fact, in one of the prior slides, when David mentioned that we had an Excel node has 2 terabytes of storage, it actually has 6 terabytes of storage in there. Only 2 is available for your use. We use the rest for mirroring and spill space. So there is a secondary copy of your data within the cluster, and the way we distribute that is, there's some smarts around that in having clicks and doing it in a way so that we can recover from failures well. So when disks go down, we have a nice way of coming back up. And also we have the ability to, and the third copy is actually stored in S3 because we take continuous and automatic backups of all your data automatically based on certain criteria that we set. So there's a primary copy, secondary copy, and your backup in S3. As I talk through these various things, one of the big things is all these nodes have to communicate with one another really well. To facilitate this, we actually have a 10 gig network that is used for internode communication that is minimally oversubscribed. Basically, that means there is little noise there, and you're guaranteed of having good bandwidth as the nodes communicate with one another. And one other aspect to note here is the security. So I mentioned one of the reasons the leader node is your only point of contact is because we don't want direct access to compute nodes that have your data. You should also note that the leader node and the compute nodes are in a VPC, and we support encryption both for data that moves in and out, as well as encryption at rest for the data that gets stored within the compute nodes. So there's a lot of other security features that you can leverage here as well. With that, let's move to the best practices portion of this. And let's start with ingestion. This is the first operation that you're likely to do when you spin up your cluster. And the goal here is, the best practice is to ensure that when you insert lots of data into Redshift, we want that to happen in parallel as much as possible and leverage all the compute nodes that are there. and minimize any overheads. So the preferred method here when you're loading in bulk is to do a copy or use the copy command from S3. So we recommend that you stage your data in S3 and then use the copy command, and when the data gets loaded, it will be loaded into Redshift in sorted order if you've specified sort keys. We also further recommend that you use a single copy command, because using multiple commands will only serialize it and delay it further, and that you split your files in S3, split your data in S3 into multiple files, because only then we can do the data load in parallel. Here is a sample copy command that you see, and you can see that it grabs the files from the S3 bucket, my bucket. You have to provide some credentials. And the other best practice in this area is when you have large data sets, please gzip them and use that to improve copy performance. So this is the recommended way for bulk loading. Now there are scenarios, and we've had a number of customers where they're not able to do this and they want to come in through SQL, through the leader node to gather data into the cluster. And this could be because they already have it somewhere else, maybe DynamoDB or in fact DynamoDB will allow copy command. Maybe you have it in EMR or somewhere else where you want to stream it in this way. For those scenarios, we recommend that if you have to use the insert command, then use multi-row inserts as opposed to singleton inserts. There is a big overhead for every statement, and we just want to amortize that over getting a number of rows inside. And on the slide there, you see an example query that you could use to insert multiple rows at a time. So the point here is try to avoid as much as possible singleton DML operations, insert, update, delete operations on the cluster. So that is the second class of things that you want to do, is bring data in through the leader node. Now if you want to just move data around the tables within your cluster, then we recommend that you use create table as or insert into select statements for doing that. All of this is documented in our guide, and the syntax should be in the SQL reference for you to look it up. Moving to the next. I wanted to make a point about loading from S3. As if you've used S3 for a while, you'll know that the S3 in US East provides eventual consistency, and what that means is what S3 guarantees is you will have all your data loaded to S3, but there may be a lag from when you load it in and when it's available to be ingested into Redshift. So, and that is only for US East. So what we recommend there is you can do one of two things. One, you can, as soon as you load your files onto S3, you can look up the listing object keys section of the S3 guide, and that provides you a procedure to verify that all the files that you think you loaded are actually available for use prior to loading into Redshift. That's number one. Additionally, you could also choose to get the data into Redshift, but once it is inside Redshift, go and query the table STL load commits to ensure that all the files that you intended to get in have actually made it in. And this will prevent you from grief later on when you're trying to do a query and some data is missing, because it could be because of the scenario. So this is just a precautionary measure. It doesn't happen very often, but something to keep in mind when you're making large loads. All right. So moving along with more ingestion best practices, these are some miscellaneous things, mostly things that we've seen customers do that have caused some pain. They don't really fall into any category, so I'm just going to go through them one by one. As much as I want to talk about what we support, I think it's important to know what is it that we don't support. So one of the things that we don't support as a single statement is the upsert statement, something you may be used to. So we don't have a single upsert statement. However, you can achieve the same effect by following a set of steps. Essentially, you will have to load your data into a staging table and then do a join with a target table. So you do an update command followed by an insert command. Again, the steps are well documented. And the other thing that has caused confusion is that we do not enforce a primary key constraint. So what that means for you from an ingestion perspective is, if you run the copy command twice on your data, you likely end up with a duplicate copy of your data in your Redshift cluster. So please be mindful of that as you're ingesting data into Redshift. So one of the things, the next has to do with the performance of the copy itself. So one of the things that is available to you is to change or adjust the concurrency in the Redshift cluster. And when you're running resource-intense commands like copy or vacuum, and you want them to speed up a little more, one of the things that you could do is to change the WLM query slot count to a low number, and I'm going to talk more about WLM or Workload Manager further down. But essentially what you're doing here is to allow only a few concurrent queries to run, 3 in this case, which means that every individual query has more resources at its disposal to complete quickly. So that's something you could use for copy. And the other aspect of performance is when you're doing big changes to your data and you're bringing in a lot of data, it's good practice to run analyze after that, just so your optimizer has access to the latest statistics that are up to date, and your query plans are optimized for your current data distribution. If you run into problems as you're running the copy command, we have a couple of things. We have 2 ways that you can look it up. One is to query our STL load errors table to look for errors. And in fact, there is a parameter that you can specify while with the copy command called max errors, which essentially allows you to ignore errors in your data and continue with the load in spite of them. And we've seen, so if you know that there are likely to be data errors in your sample set, you may want to set this to an appropriate number. And the other way you can look at errors is also through our console, and I have a screenshot in the next slide. One thing I want to mention is the character set that we support. There's been some amount of traffic on the forums regarding this as well. We support UTF-8 only up to 3 bytes, and there are special characters that we don't support, and these are documented, so please do take a look at that as you're trying to figure out what might have caused problems during your data ingestion. So moving on to the next slide. So this is a screenshot of our console. It's not very readable. I think I just wanted to put in a plug for the console. We do have a fairly rich set of functionality in the console. You can use this to view errors. There is an entire panel that is dedicated to understanding query performance, understanding how CPUs are used, etc. So if you've not done so already, please leverage the AWS management console for Redshift to really understand what is going on with the operations and queries that you're running. Okay, so that was all about ingestion. Let's move on to figuring out how we set sort and distribution keys. So one of the things with Redshift, it is a managed service. So there are very few knobs that you as a customer have to set in order to get started. At a high level, there are probably 3 things you're going to do up front. One is to figure out how many nodes you need based on how much data you have. And the other 2 would be figuring out what your sort keys are for your tables and what your distribution keys are for your table. The next couple of slides, the intention here is to just help you get started on how you can think about setting these keys and provide some guidelines on how you would go about doing it. The treatment here has been somewhat simplistic, and the reason for that is there's some confusion as to how to get started, and that's what we're trying to address. In reality, it's very possible that the queries and workloads are fairly complex, so you have to take into consideration other factors beyond just what is here. So typically, when you think about sort and distribution keys, you would look for all the join requirements, all the filtering requirements, because these determine how you distribute stuff so that things can be co-located. You have to look at the size of your tables, and why that's important is, smaller tables can be shipped around nodes, and that's still okay, but the larger tables you want it to stay put. You want to look at the cardinality of your columns. If something has a large skew, you don't want to distribute on that. If it's like a primary key and it has even skew, then that's a good choice. So there are several things to think about, and there are likely also going to be some tension in which key would be better because of the complexity of the queries. So some of our more advanced users have actually gone down the path of experimenting with different sort and distribution keys to figure out what works for their applications and what works from a business point of view, because you may not be able to optimize for all the queries, but at least the ones that actually are critical to your business you want to optimize for. So with that background, let's get started on the sort key. So the goal for the sort key really is to skip over data blocks to minimize I/O. Now David touched on this briefly when he mentioned zone maps. So within the Redshift clusters, we maintain when you choose to sort on a particular column, we maintain the min and max values for the blocks that are stored within that node. And this allows us to completely skip over entire data blocks when we know that you're filtering on that and we know the range that you're going after. So that's the role of the sort key, and you can actually specify more than one sort key if you'd like. So the way you'd go about picking one is to look at all your queries and look for the where clause or the filtering that you do, and pick those columns that often get filtered, because that allows us to skip over things that are irrelevant to that query. Very often we see a good sort key would be to use a timestamp as a sort key, and the reason for that is there is a tendency to query data that just came in the last day or the last week for BI applications, and that typically ends up being a fairly good sort key to go after. In terms of trade-offs, when you pick a sort key, what we have to do while ingesting data is to sort it before we write to disk. New rows that get added are temporarily stored in a region that is unsorted, and the vacuum command will get it into a sorted format. So there is an overhead to keeping it sorted. So just be mindful of that as you pick your keys for sorting. So the third thing that you pick, so number of nodes, sort key, and the third thing is the distribution key. The distribution key is used by Redshift to figure out how to distribute the data for the tables across all the different nodes. Now, if you go back to our architecture, one of the things I mentioned is we try very hard to engage all the nodes and all the operations and keep things going in parallel. So the distribution key has a couple of key goals. One, of course, is to distribute the data as evenly as possible across the nodes. And number two is to minimize data movement among the nodes when we are executing a query. So for example, when we have to do joins and aggregates, it's much better to have them happen within a node than to ship them across the network, because the network cost is fairly high. So these are the motivations for how you would go about picking a good key. So the best practice around this is the first thing you should look at while trying to figure out your distribution keys, look at your join clauses and figure out what you typically join on. And sometimes you have multiple joins for the same table, and then a good choice would likely be the foreign key of the largest dimension that you're joining with as a distribution key. Again, the reason that is that you don't want that to be shipped around. Now, if you're not very heavy on joins, but you do have aggregations and group by, the next thing you can look at is to look at your group by class and figure out, and that could be a good column to go after as a distribution key, because you can do the operation within the node, the aggregation or whatever function you have in place. And things to avoid here would be equality filters as distribution keys, because what that will do is when the query comes in, you're going to have one node that fits that criteria, and all of that, and you get no benefit from the parallel, from having all these nodes available to you and parallelizing that operation. So that would not be a great choice. And the other thing is sometimes it's not very obvious, even after looking at all of this, it's not very obvious what a good distribution key should be. Or maybe you have denormalized tables and you're not doing a lot of aggregates. In that case, it's best to not specify one, because Redshift has a default distribution scheme where it just uses a round-robin way of distributing all the data across all the nodes. So that's also available to you. So In this slide, you see a sample query that you can run. So as you experiment with different keys, one of the things that you want to keep your eye on is the skew of the data. This is a query that you can run that goes against the view SVV disk usage that gives you the distribution of the data across all the slices. So in this particular example, you see that it's fairly well distributed. You have about the same number of values across every slice, and this is highly desirable. And here I have an example. This is an oversimplified example just to drive home the point of how do you go about looking at your queries. So in this case, we are trying to figure out the total produce sold in the state of Washington for January. And the first thing we want to do for a distribution key is to look at the join conditions, and over here we have category table being joined with the sales table based on product ID. So I like the product ID to be co-located, so I picked that for the category table. And on the next step, we have the franchise table that is joined on the franchise ID, so pick that for the distribution key for that. And for the sales table, I have a choice. I could go with product or product ID or franchise ID. In this case, I chose to go with the product ID because product is the larger of the two tables, and so I want that to be co-located more so than the franchise. And finally, in the bottom, we have a filtering clause based on the date, and therefore I'm going to go with that as my sort key. So fairly simplistic view. I know the real life examples are far more complex, but at least gets you started on what to look for. All right. So other things that impact query performance. So sort key, distribution key will have an impact on performance. The other things that we've seen come into play is that so the first thing is about encoding. So one behavior that we've seen is a lot of customers tend to use the character data type for encoding date and timestamps. We would strongly encourage you to use the timestamp data type because it's far more efficient from a processing perspective to use this rather than character. So please change that if possible. And the other one is about constraints. So I did mention earlier that we don't enforce primary key constraints. In fact, we don't enforce primary key, foreign key, or uniqueness constraints. However, we would like you to specify this in your definition because the optimizer still uses it as hints to generate the query plan. So do specify them. Of course, the thing to remember here is that your loading procedures and applications just need to be aware that these are not enforced so that they can compensate for it. The next point is about specifying redundant predicates on the sort column. This is not a great example, but essentially the point I'm trying to make here is that sometimes you have queries where you're joining certain tables and filtering, and there is an implication that there are some redundant filters in play there. We will not be able to pick it up, and the suggestion here really is just to say that if there are implied filtering criteria that you see for your queries, just go ahead and explicitly specify them as part of your query because that can speed things up because we don't have to read through a lot of the I/O blocks. So that's on that point. And the last point about performance tuning is about the Workload Manager settings. So let's look at the Workload Manager. So the Workload Manager, well, we have one, and it essentially allows you to manage and adjust your query concurrency. So the Workload Manager essentially lets you dial up the number of queries that can concurrently be running in your Redshift cluster up to a maximum value of 15. The default settings, I think, is set to 5 concurrent queries. You can set it up to 15. Essentially what happens is all the available resources get divided into as many number as the number of concurrent queries you want running, and it gets divided equally among all of these groups. Our WLM also allows you to define user groups and query groups. Essentially, with user groups, we identify queries coming from certain users to belong to particular user groups and queue them accordingly. And with query groups, you can actually label queries and give them labels that point them to a particular query group and directs it to the appropriate WLM queue when it comes in. Very often, the practical application for having setting up WLMs is to segregate short-running and long-running queries. So you probably have some really large reporting queries that take a long time to run, and then some ad hoc queries that are fairly fast to process. And you don't want to have your tiny queries get starved because the other one is just taking way too long. So you'll probably want to set up different queues for these based on their expected execution times so that you can keep overall throughput at a fairly high level. The other way you can use WLM is to help improve performance of individual queries, and this is something we touched on with the copy command, is you can set this to a low value just so you give certain queries more resources to complete quickly and get its job done, and you may want to do that for copy and vacuum and commands like that. One thing to be aware of is a lot of the other OLTP systems allow a high degree of concurrency. The architecture for Redshift is really geared towards processing large queries with a lot of data in a very short amount of time. So as you try to adjust these parameters and figure out what is the right values for your system, it's also important to keep in mind that you measure the overall throughput of your system and not just the concurrency, because the cluster can process big queries very quickly, and sometimes it might be better to have a lower concurrency setting just so these queries get through than trying to max it out. So I would say as you make your measurements, just keep an eye out for the overall throughput as well. And so we have seen examples where the overall throughput in fact increases when you reduce the concurrency. So something to keep in mind. All right. And here is a screenshot from our management console that has the WLM settings. It's fairly simple. You just have to set the concurrency, and you can go up to 8 queues total. However, the concurrency says at 15, so all of that has to add up to 15. Your default is 1 queue with 5 concurrent queries, and beyond the 15, we actually have some slots available to us so that we can manage your cluster. So you can set up user groups or query groups, and things will get queued up and routed accordingly as they come in. So that pretty much completes all the best practices that we wanted to cover in this session, because we wanted quite some time for the Q&A portion. The key takeaways for this would be to avoid, if possible, large number of singleton inserts, updates, or delete statements. They don't do very well. Try to use the copy command for uploading large data sets. Use gzip and split up your the files for the copy command. Choose your sort and distribution keys with care, and likely this is going to need some amount of experimentation and with different settings to get the right balance. And yes, please encode your timestamp data using the timestamp data type. That will have an impact on performance. And finally, we have a workload manager. Leverage it if it makes sense, and again, that will also probably entail some amount of experimentation with what really works for you. Thank you. I think we'll go to the Q&A portion of this.
Yeah, thank you, Vidya. So just a quick slide here with more information. We don't really expect you to remember the long URL, but you can just go to the AWS homepage /documentation/Redshift. You can find all the documentation there. The developer guide is in particular the most popular by a long way, and both of these links point to that guide. So please visit there. So we're going to just pop up a quick survey so you can give us some feedback. And now we're going to launch to questions, and we've got other members of the development team here as well. So let me just, please, if you have a question, just refer to it. Just go to the Q&A tab down the bottom of your screen and type in your question. We do have a lot of these, and we'll get through them as fast as we can. Those that we don't, by the way, these questions are great. These feedback or questions in general, even if we don't get to them, what we like to do is take this sort of information and populate our FAQ. So please visit the FAQ. We do update it regularly. These sort of sessions are great feedback for that. So let me call out the first question. Is it possible to change the distribution key on a table that already exists and is populated with data?
No. You would have to create a new table with the new distribution key, do insert a select, and then you can rename the tables back and forth to achieve your result.
Great, thanks for that. Is it possible to define several single sort keys for different fields versus one sort key? I'm sorry, the question's just disappeared on me. Versus one sort key, including more than one field.
No, Redshift only supports one single sort, which can be a compound key or a single key. We don't have the concept of secondary indexes or projections or anything like that.
Great. Sorry, the questions are jumping around on me. I'm using single node cluster, and query performance of my queries sometimes is better on the largest sets of data. So let me try to highlight that. There is no concurrency at the moment. Could you explain? So the larger sets of data, table structures, compression, and keys are the same. There is no concurrency. I don't think it's immediately obvious, but please, we do like to hear directly about these ones. If you do have something that you're not quite sure of, the purpose of these sort of best practices is also to help answer a lot of the questions that we've got through the forums and directly to our support teams. But if there's something that we haven't covered, feel free to provide specific detail, and we'll get the team to get back to you on that.
Yeah, on that one we would have to dig in further to look at your tables and see what's going on.
Can you comment on the performance of joins on large tables versus using a single denormalized table? How does that compare?
Well, a single denormalized table will have advantage that you don't have a chance to have a non-collocated join, and because it's a columnar database, you're only going to select the columns you need. The problem with that approach is that you force yourself into a single view of your data with a particular predefined join of your denormalized data. So if that is acceptable for your project, it is a way to speed up your queries. Normally the best performance we see on customers is they do a selective denormalization of some columns that join together that they cannot distribute with the same key, and that hybrid approach usually is more helpful because it becomes more flexible over time as your business grow or your questions from your data changes.
Thank you. So here's a question about the Workload Manager. If the settings have not been changed and the customer is only running one query at a time, do they get all access to all the resources, or do they have to change the WLM to improve that?
Well, the CPU power, yes, it's used. Every query tries to use as much as availability of the resources available, except for memory. So one thing you're leaving on the table right now is the amount of memory is given to a query, which can make significant difference on performance. Instead of setting concurrency to 1, because that would cause you to not be able to run a side query to check the status of your queries and this kind of stuff, since the default concurrency is 5, for your particular large queries, you should set the slot count to a number like 3 or 4, and then you use more memory, 4 times memory than usual, and you still leave one thread available so you can log in and see status of your queries or status of your loads and things like that.
Great. Is it possible to load files directly without going through S3?
So yeah, you could comment through DynamoDB. We copy directly from DynamoDB tables. Load to all the nodes, then the two ways currently we support would be DynamoDB and S3.
Yes, I think the distinction there is on parallel load. You can of course move data into Redshift using the SQL gateway, but that will be serial, and that's why we ask that you do multi-row inserts if you do that approach. So that's okay for small sets of data. For large sets, it's better to push them into files on S3 and copy them in. So do you have any best practices for moving data from DynamoDB to Redshift? I might take that one. So copy from DynamoDB is direct, as it is from S3. It is table level at this stage. So really, it really depends on the type of data you've got in DynamoDB. If it's time series, for instance, you may want to structure your DynamoDB storage so that you have what we call kind of rolling tables, where you have a new table for each period. And as the data ages, the throughput allocated against that data can be reduced, especially the write throughput. And that's then available for kind of read and ingestion into Redshift. This is a popular use case scenario where Redshift is used not only as the analytics store, but as the place to archive Dynamo data. It's also much lower cost to drop a DynamoDB table than to delete all the objects, as it is in any database. So most of the best practice tends to be on that side of it. We are moving towards more formal documentation and workshop sessions to cover these sort of aspects in more detail. Thank you for your question. In a typical data warehouse scenario, we need to migrate update data from operational databases to Redshift nightly. However, updates and inserts are slow, and we would prefer to only migrate the delta. What's the best practice here?
So what you could do is to have on the Redshift side two tables, one for the long-term data, like let's say, for example, 15 days old and older, then a more recent table, and those being a smaller table when you load nightly and you do your vacuum and you analyze, your queries will go against both tables, or if your application can be configured to know if I'm looking for short-term or long-term queries. And over time, you can migrate the data to the Redshift, because appending to the end of the tables, assuming your sort key is by time, it will always be less expensive and easier to maintain than any other way. So the likelihood of updates happening on a data older than X would decrease over time, depending on your business. Like for normal web applications, would be like about 15 days or 30 days, no more than that.
Good, thank you. So is Redshift distribution aware? Does it support co-located joins?
Yes.
Absolutely, and that's the point of the distribution keys, is to ensure that you have as many co-located joins as possible for your complex queries.
Can you please talk more about Redshift's implementation of zone maps? We may have covered that after that question was asked, but do you want to just quickly talk about the skipping?
Sure, we talk about it as if it's a zone map, just because it's a concept that's familiar to everybody. Essentially, at the node level, we store, when you sort the key, sort one of the columns, we track the min and max values that is stored, and we track where it is stored. That way, when a query comes in and you're filtering on that particular column, we're just able to skip over all the stuff that's not relevant for that query. So pretty simple implementation.
Yeah, definitely use your sort keys as much as you can. So a question about standard ETL tools such as Talend, Informatica, or DataStage to load the data. So quick comment on that. We've already announced several partners on the ETL and many on the BI side. So on the ETL side, both Informatica and Talend have actually formally certified their integration with Redshift. DataStage hasn't yet, but all of these are in process. I think the important point is, the Redshift is kind of decoupled from the ingestion phase in that you have that SQL gateway, but also you have S3, and that's the preferred way to do even incremental ingestion, because it's just way more efficient. So in general, these tools all support that architecture, in that they can output to delimited files and make that work. So yes, if you need a specific technology that's not mentioned on our web page, and we do have a list of those that are certified, if it's not there, please get in touch with us and we can work with you. So the answer is yes, it will probably work. 99 times out of 100 these work, because we've got very standard interfaces. Certification is a different process, where the vendor who provides the technology needs to walk through a series of certification steps. So we're working with them all on that. Sorry, we had a few people with a couple of problems. Is a slice equal to a node?
So a slice is, a node is comprised of several slices, and a node can have multiple cores. The difference between a node and a slice is specific to a single core. So it has a core, and then it has a memory and disk. So you can think of a slice as a smaller granularity, and several of these make up the node.
Great. Yes, and actually the top of the documentation, there's a pretty good discussion on architecture there, and the notion of a slice is fairly well explained. So we do encourage you to look at that for more detail. Another question, is it recommended to specify an aggregation column as a distribution key if the data is not evenly distributed across the values in that column?
No, not really, because you incur the risk of having that being the fact make your table not distributed in the same amount of rows on each node.
So in general, with distribution keys, you're going to have some tension between all the different things that we talked about. So with keeping the data even, keeping the joins co-located, and having aggregations co-located. So it's almost in that order. You want even distribution, you want to focus on the joins, and then look at the aggregations.
Right, just to add some more color there, the reason you want the even distribution is you want to balance out the processing across all your nodes. So if one node is doing more of the work, it becomes the bottleneck for the overall query.
Great, thank you. So we did have a question about data pipeline, and why didn't we mention it, which is a great point. For this best practice, we focused on data ingestion, really the direct ingestion from S3, and we didn't even cover DynamoDB except to say it's also managed by a similar approach. With data pipeline, it facilitates more data integration from other sources. So data pipeline, if you're not aware, is a coordination scheduling capability that allows you to coordinate AWS resources to really minimize cost and increase, through automation by decreasing the amount of effort you're applying to do that as well. So that will definitely come up in a subsequent webinar that we'll be doing on data integration. But great question, thank you. Do you have performance comparisons against, well, in this case, SQL Server? The general answer is we don't publish that stuff, but we do have plenty of customers who are vocal on that. Our general guidance is for a row-based data store like SQL Server or MySQL or Postgres or Oracle, you will see at least a 10x improvement in performance simply by the nature of columnar storage. It gives you that sort of advantage over it for large scan-based queries. So yes, that's something to be expected. We do see a lot higher, and our customers are fairly vocal about some of those performance gains as well. Is the date type equivalent to timestamp with regard to query performance?
Not really. The size of the field where it has stored in the database is different, and the granularity is different. So depending if the column is just returned, the difference would be minimal. If the query is used for a distribution of data or sort key or distribution key, then the difference grows bigger. You have to understand on each position the column is used and which role that column makes during the query processing to be a different. Yeah, the timestamp would be a higher granularity. So it's a good sort key. If you have one or a single sort key, if that's part of your problem, a regular date might not be a very good sort key because the granularity is about a day. So you have to take into consideration those two things.
Great. And so is the 15 query concurrent limit per node or per cluster?
It's per cluster.
But isn't that per queue as well?
It's across queues.
Okay.
The total across all the queues.
Got it.
So at a time, you can have 15 queries running concurrently within a single cluster.
Great. If doing a star schema, do you suggest loading the data into a staging table, then doing the roll-ups into dimensions, then insertion into the fact table?
Well, if you can have your data on S3 already in the shape that you want it to be, right? You do the load straight to your star schema tables. If you have to do your roll-ups in the database, you can do rollups inside Redshift from temporary tables, which will be very efficient and fast if you match the distribution keys and sort keys of both the rollups and the original tables. It will be a fast process of doing that. You can even have like a temporary table created to do as your load process to do that as one step.
So it's not so much dependent upon whether it's dimensional fact table. It's more about how much processing the data needs to undergo before.
Right.
So Redshift is agnostic to the fact that these are fact tables and dimension tables.
Okay, great. Are there tools for evaluating performance characteristics and providing suggestions for improvement?
We have a fair bit of performance data that we provide as part of the management console itself for individual queries. I don't know if this is other tools beyond.
Yeah, so I think there are third-party tools, and we'd probably do something on that, performance tuning in general. We do have a performance console, which is great for isolating runaway queries and just understanding when a query consumes, even if it's not consuming too much, to understand how much resource the query does consume. So that is excellent, and there is actually a guide in the book to see if your queries are spilling to disk, which is pretty much the most concern that you should have about a query, because that could be a query problem or it could be a configuration problem. And so if that's occurring, then yes, you'll definitely have ways of and guide to improving the performance of those queries that do. And you'll certainly be able to monitor it and understand where it's going wrong. So we've got a couple more, time for one or two more. Do create table as select operations automatically compress columns like copy operations do?
No, it does not. No, it does not. The best way of doing that is for you to either pre-create the table and load it after you already define the compression, or you load the whole table and analyze compression on the table, and you give you the most optimal compression for that table, and then recreate the table with the new parameters. The create as select, given the same distribution key and the same sort key, is very, very fast for very large tables.
Got it. So can I use the copy command on multi-part gzip files? Also, going by the 2 gig file size best practice guideline, is it the raw data file that has to be 2 gig or the compressed gzip file that has to be 2 gig?
It is the compressed. It is a best practice related to how S3 works on files. Every file bigger than 2 gig on S3 will have to be break apart to be uploaded or downloaded. So it's based on the compressed file, and you cannot copy from a multi-part gzip files unless the breakage happens exactly on a line limit, which won't happen on a gzip file.
Great. And on the 2 gig, is that actually a limit or it's just a recommended?
Just a recommended.
Yeah. So you can put bigger, but you will get inefficiencies. So 2 gig a second is kind of the optimal rate there for data coming out of S3. What is the recommended approach for loading small numbers of records under 10,000?
Accumulate over time and then load at once. There's a kind of a set cost to make a load statement. So sometimes a load with 10,000 rows or 100,000 rows will take the same time. So with that in mind, you have to choose your latency for the data to be loaded and how much time you spend loading the data based off of that, right? The more you batch together the loads, the more efficient you will be, but then you incur more latency on the data being available on your Redshift cluster. So it's something you're going to have to decide in terms of business related and ER efficiency you want to have on your system.
Great. I think we answered that. You mentioned parallel loading during the copy command. Is there anything that I need to specify, or is parallel method invoked automatically?
The parallel happens automatically. The only thing that would prevent the load happening parallel if you have a single file to load on S3. You would have a good number of files from S3, and then we spread the files per slice to be loaded over time.
Great. A quick question, do we do TPCH benchmarking testing on Redshift? I mean, the answer is absolutely yes. Do we publish that? No. And the reason is because, there's a couple of things, and I talked about the agility of Redshift as well as the cost. With the agility, it allows you to test Redshift on your own data set, which is way more meaningful than a third-party benchmark. So often these benchmarks are relied upon as a pre-step to bringing your own data in to make sure that it's at least in the ballpark of performance for you to undertake the cost and effort to even run a proof of concept against your own data set. With Redshift, that's different. For 85 cents an hour, you can spin up a cluster. It'll take a few minutes, and then you apply the best practices for ingestion, bring in the data you need, and then start querying and running it. And of course, play with the distribution keys, play with the sort keys, and optimize based on those data sets. That's absolutely the best way to do a proof of concept, and the most meaningful statistic you'll get for performance is your own data. So thanks for the question. I think we have time for a couple more, one or two. Oh, we're actually over. Let's take one more. Console's stuck. What's the best way to get data from RDS into Redshift?
Ooh. Well, RDS can mean 3 different databases. So right now we don't have a very good satisfying answer to that. We've seen customers write applications that would read data from whatever the RDS database and pipeline into Redshift. I've seen customers dumping their data and loading to S3 and then loading into Redshift. That's the most common way, especially if they're gonna load like a day or a couple days worth of data from the database into the Redshift. They normally create files and load that into S3, and then from there to Redshift, which helps them with faster loads, and also they have like a second. The data is also stored in a second place as well while they load, if they want to revisit the data or check for any issues over time.
Great, thanks. Yes, and I think we've got a lot of questions on roadmap, which we don't go into. We don't talk about futures, but I think it's fair to say thematically we're always looking at ways to do better ingestion, faster and more versatile, so more sources. So it's safe to say that RDS is a focus for that sort of activity, as well as, of course, performance of general operations in Redshift. You may have understood the theme that performance is a very important part of Redshift. It's true, and we continue to work on that. It can always be better. So with that, I think we're out of time. We're actually over a little bit, so I appreciate everyone staying on. Thank you for your time. We will take all these questions and, as I said, populate the FAQ for things that are recurring. So stay tuned for more Redshift and other webinars from the database team, and we'll see you next time. Thanks very much.